close the long session of speakers. Lucky enough, we have one missing speaker, otherwise we would have gone over time and breaking also the discussion time. We actually have 5 minutes of time left. We can decide to all go for a coffee break, or we can also decide to, perhaps if somebody has some leftover questions, this might be the good time to actually pose those questions. We have been talking of very different systems. We have been talking about biological systems like the exosomes. We have been talking about artificial man-made nanoparticles, lipid-based, solid materials like iron oxide. We have been talking about polymers. We have been talking about macro-scale objects for implants. We have been talking about nanoscale objects that can be injected. How do we find a unifying element among all these topics? How do we find basic physics that can actually regulate the mechanism of these particles? We can continue with this philosophy all the time. So if you want me, I can push in that direction until the 8 p.m. Or again, we can resurrect questions that have been left over from previous talks. Please, thank you for saving me. Otherwise, I would have pushed it to the 8 p.m., really. It's a fascinating topic. Please.
Hello? Yeah, okay.
Since you have been posing a lot of questions, why don't you introduce yourself and you tell us where you come from?
Exactly.
It's
I'm
already
Ivona
part
Cicha.
of...
I come from Erlangen, University Hospital Erlangen, section of experimental oncology and nanomedicine.
Fantastic.
And I have a question to Dr. Corin about the shear activated particles, because I was really greatly impressed by your original paper. And if I remember correctly, you mentioned there that about 100 dynes per square centimeter was necessary to activate those particles or the aggregates. Do you expect that it would also work in humans? Because in mice, the shear stress levels are enormously much higher than in humans. So what is your estimate and potential clinical translation?
Corin, Nati.
Okay, thank you for the question. Actually, we designed them for human shear stress. And the mice models are not ideal for that, that's for sure. But you know, when you go through the process of submitting something, you have to stick to known models that are existing in literature. So this is why we started with the mice model. We show that it works. We can tune these properties, but we know that for human, we have to reach above 100 dyne per centimeter square is pathological, and below it is you can reach in normal conditions.
Okay.
So we know this threshold, then we did mice, and then we moved to rabbits, where the shear stress is more similar.
Yes.
And the future is to try it in larger animal models. And also in parallel to doing these assays, I didn't have the time to show, we developed in vitro assays for doing them in reconstruct. I just showed the bifurcation, but we do reconstructed stenosis based on scans and do it in vitro, and now we can function like
them. So like 3D model?
Yeah, 3D printed models that we do, based on them we form transparent models, and we can put cells and form localized clots there. This is where we're going now. And looking at it in like real patient-specific
you can take patient-specific geometry for that.
With blood flow and measured hemodynamic conditions as inlet conditions. But it's not done yet, so I cannot.
Yeah, that's great direction, I think.
The 100 dyne per square centimeter is a sort of cutoff in humans between physiological and pathological flow conditions.
Yes.
Am I correct?
Yes, this is the
That's
cutoff.
basically the way it has been identified, a cutoff.
Yes. And in severe stenosis, you can reach 1,000, so it's way above. And I think there is a gap also in this general field of gapping human disease models. You know, you can do a lot of things in animals, which everybody here loves, but they're not that
close to the
correlate with the problem you're looking at. So we're working a lot on models that we think are new, and people also do. I come from the microfluidic field, a lot of that. But let's say in large arteries, these they do not tell the
of
story.
course.
Like,
Yeah, that's the other story, different flow conditions. Yeah. Thank you very much, but it's really
Let's,
very impressive
okay,
work.
thank you guys. Let's change topic. We have had two talks. One was the talk from Andreas, who was emphasizing the ability of polymers to change their shape based on inputs. Inputs that was a thermal input that should come probably from inside the particle, for instance, some iron oxide or some gold nanoparticles that are basically dispersed within the matrix. Now, switching on and off a alternating magnetic field, I mean, it's already alternating, so in a sense, it's already on and off. But you want to control when it's on and when it's off, rather than being always on and off, on and off, and on and off. So probably a laser application where you can immediately shine the light and in that specific instant induce the heating or overheating of the iron oxide nanocubes or the gold nanoparticles could be the best way to go. I guess iron oxide probably better than gold. Gold will burn everything most likely because the increasing temperature that you're gonna induce will be damaging permanently the polymers. So I don't know if you can expand, if you can guys expand a little bit on that, if there is any application that you have seen already, tested already in this direction.
Well, the materials are so new that we have not yet put them, that we did not yet put them in the human body.
Yeah.
So one direction where it really develops to is robotics, because robots need muscles and robots can be very small. So I looked very much forward to the nanorobots. It will not be nano, but it can be a micro. Light is a possibility, especially near infrared light, but we are also intensively working on ultrasound, which also works very nicely. It's interesting.
For inducing the transition.
For introducing the movement, yeah.
Thank you. Perhaps one closing comment on the work on Wanjin. So the selection of the nanotubes for generating these nanorobots, basically, if I have understood correctly, they open up when they reach the tumor vasculature and they basically interact with the endothelium, right? So, but you have selected the carbon nanotubes for any specific reason, or it could have been also other materials that, based on the interaction with the through the specific ligands, would open up and expose thrombin to the blood flow.
Yeah. So I think this is a very cool question. So I have two aspects I want to emphasize that, because I think people familiar with nanorobots, I think back to 2012, there's a group in US, they propose using DNA origami, like it open like a chair, open and close. But that one only work in the cellular level. They cannot achieve in the in vivo. So that's very challenging, because our nanorobot is open, close from the closed stage to open just one binding event. So basically that's very simple. So if we want to show this really work or have very strong effect, this one have to be very dramatic, amplified signal. So the blood coagulation is really good example, because it can be amplified many times.
Naturally,
so that's why
yes.
we can see that effect, anti-tumor effect in vivo. So in terms of the shape, why we want to have the nanotube instead of other structures, because people know basically based on the DNA origami, you can make any different sophisticated structures. Can be make like a box, can make like building, whatever the structure you can make it. But for us, we have to make it can be closed, but can be opened, easily opened. But if you close too much, cannot respond to the local environment, so they cannot trigger as a nano machine. So that's balance the specificity and also the open up potential based on the binding. So we choose the tube, because the tube have certain tendency to open up, because there is a physical tension there. If you open it, it's like the purse, like ladies' purse, you can close it and open it. Yeah, so there is certain physical tension there. But certainly we can do many other different morphologies and structures. But there's something undergoing where we try. People say there's, as long as you have your imagination, there's no limit for nanomedicine. You can design whatever things you want to.
Andreas, you want to
Maybe
add?
just a question about robots. So I learned from the robotic community that robots can move always in both directions. So can the tubes open and close without a help?
Yeah, if you're talking about the machine, people always thinking about the close and open. I think if you think about the 2 years ago, the Nobel Prize for chemistry is go to the molecular machine. They can, if you set a light on the molecule, they open and close. That's reversible. Because for us, it's happen in vivo, so you don't need to close and open, because when they open, it's have a very strong biological effects. So there's no way to go back, and you don't need to go back. So for us, it's a one-time open machine, yeah. But if you think about other applications, for example, you repair the damaged tissue or deliver some, for example, molecular probe, in certain circumstances, probably you need open-close multiple types, but they will be more difficult to achieve, I think.
I have one last comment. I'm taking the liberty to not asking additional question from the audience at this point. And I was wondering, listening to the talk of Georgia and the talk of Beatrice, right? Having a scaffold that is somehow enriched with exosomes, which carry some specific information to those mesenchymal stromal cells, what do you think could happen? Very open question, even more imaginative than one gene.
It could be a great option, because at the end, we are using just the scaffold for delivering factors. So the mesenchymal cells are delivering growth factors. So if you can use the collagen, which is covering the whole surface of the infarcted tissue, to deliver these exosomes, that will help to repair that tissue. So I think it's something that we have to think about. So.
And it's not a systemic delivery, so perhaps all the issues related to heterogeneity can be zeroed by that. I don't know.
Yeah,
Georgia,
yeah,
yours.
it depends. But talking about heterogeneity, I want to touch a little bit. Exosomes per se have been used in the clinical trials, phase 1 at least. So the heterogeneity is not limiting their application. Having said that, you brought up a very important point, and that's where I think, while it might add value having the incorporation of biological heterogeneous system, is also important to try to control it in such a way that, for example, I didn't have time to share, but we need to control how the membrane doesn't flip, and therefore you don't have problem of immunogenicity.
Yes.
There are ways of doing that, but requires a lot of effort and characterization. So it's a stiff curve, but might provide in long-term advantages.
Yeah, clearly a simple process, but there are a number of hidden secrets that we'll learn more about that probably in the near future. Okay, it's now getting to 8 p.m. as I promised, so we're finishing here. Thank you very much, everybody. Thank you.